There are two logarithms that are programmed into your calculator. When you see a button that just says log, that automatically means a log base 10. So if you want to calculate the log of 100, the common log is log base 10. So if there is no base written here, it's automatically understood to be a log base 10. Exactly the same way that a radical with no index is understood to be the square root. So if you want to know what the log of 10 is, that's going to be 2. You can do it because we know that 10 squared is 100. Therefore, the log base 10 of 100 is going to equal 2. But you can also locate the log key on your calculator, and just depending on the calculator, you may type in 100 and then hit the log key. If it's a standard calculator like this, so if I put in the 100 and I hit the log key, it just pops up with 2. I don't even need an equals. This is great because then if I need to know the log of 3, what power does 10 have to be raised to make it equal 3? Then all I have to do is hit 3 log, and I get that it's going to be 4.4771, and they usually run them at about 4 decimal places. If I need to know what the log of 524 is, I just type in the 524 and I hit log, and it turns out to be 2.733 and a bunch of 9s. Well, 3 of them, and then a 287. So to 4 decimal places, this 9 would round it up. So this goes up to a 0, which causes that to go up to a 0, which causes that to go up to a 4. In other words, if you take 7,399 and round it up 1, it has to go to 7,400. So this is 4 decimal places. Now the other log that's programmed into your calculator is the natural log. And the natural log is called because it shows up so much in nature. It shows up in constant compounding of interest, and that is the base E. Instead of calling it log base E, they write it as ln, L and N. And sometimes people will see this, and if it's not written as caps or in cursive, then it'll look like IN. And so this, sometimes people interpret that as an IN or a 1N, but it really means an LN. So if we want to know what the log base E of, I don't know, 52 is, that's the natural log of 52. So now in a graphing calculator, you're going to be putting in log and then type the 52, or you're going to put in natural log and type in the 52. In a standard scientific calculator like this, you'll probably put in the 52 and then hit ln. And that turns out to be, to 4 decimal places, 3.9512. There is also a change of base formula, which is going to come in really handy about now. The change of base formula will let you calculate the logarithm with any base of any number. And it's because the log base b of a is the log base c, some other base, of a divided by the log base c of b, the original base. So this will work for a common log. So you could do the log of a divided by the log of b, or you could do it natural log of a divided by natural log of b. It doesn't matter which key you need, you can hit either one. So if you need to know what the log base 3 of 81 is, and you don't realize that 3 raised to the 4th is 81, so I know this is going to come out equal to 4, then I can either put in the log of 81 divided by the log of 3, or I can hit the natural log of 81 divided by the natural log of 3. When I put this into the calculator, since this is a standard calculator and I put in the number and then I hit log, I will enter this as 81 log divided by 3 log, which will give me the logarithm of 3, and then I'm going to need to hit the equals. Now we already know the answer is 4. Always figure out how to use your calculator by doing a problem that you know the answer to. So I hit 81 log, gives me the log of 81, divided by 3 log, gives me the log of 3, equals, and when I hit the equals, it comes out to a 4. In this formula, A is going to be the number of atoms of argon 40 in the specimen. K is going to be the number of atoms of potassium 40 in the specimen. Now we're going to do this piece by piece. What if the ratio of argon to potassium from a certain specimen is 0.2122, sorry. Okay, so they're giving us the ratio, the entire A over K. So let's see what happens. We've got T equals, we'll use this last, 1.26 times 10 to the 9th. We can actually enter that in the calculator just like this, times the natural log of 1 plus 8.33 times 0.2122 divided by the natural log of 2. So I'm going to figure out the numerator here. So first of all, I'm going to work this out. I would not attempt or suggest anyone else necessarily try to put this whole formula in your calculator at once. To me, that's just asking for trouble. So I'm going to follow order of operations. I've got 8.33 times 0.2122 equals 1.767626 plus 1. Now I'm going to go ahead and write this down. I'm not going to clear my calculator. So when I add the 1, I get 2.767626. I'm going to get the natural log of it. So let me start another line here. This is going to be 1.26 times 10 to the 9th. So I'm going to get the natural log of this, which is already in my window, divided by the natural log of 2. So the natural log of that divided by 2 natural log equals, remember, it's not going to do the division until I hit equals. Oh, this is times 1.4686. I'm going to round that to 9. Then I want to multiply this times 1.26 times 10 raised to the 9th equals, and I get 18504977739. Not a decimal in sight now. This is actually the number, hundreds, thousands, millions, billions. $850 million 497,000 739, but they're asking us to get the age to the nearest hundredth of a billion. Hundredth of a billion. So we've got 1 billion or 1.850 billion. Lots of other decimals. The nearest hundredth of a billion would be 1.85 billion.